Hello, everyone. Whether it's morning in your place, evening in your place, whatever it is, what joy it is that we can gather together to celebrate 40 years of World Scientific. And we all should know that World Scientific has established itself in the, publishing realm, that these big guys, North Holland, at one point says, I want to buy you. And KK was indeed strong enough to say no, because the big guys, they just want to crowd you out so that they own the whole field of physics journal so that everybody around the world will know what is going on in physics. But there are many scientists elsewhere that are not exposed or not able to, like Bose, Bose-Einstein statistics, and so on. But I think it would be good for us to first hear how C.N. Yang and Abdul Salam encouraged KK Phua in Singapore to start World Scientific. So I have the pleasure of introducing my friend, my close friend, KK, for him to say a few words on how World Scientific started. KK? Go.
Hi. Yeah. Good afternoon, everyone. I think World Scientific actually started by Professor Abdul Salam, because Salam has always have an idea to start something outside Europe and US. So he mentioned to us, to me, many times that we should start some journals or book series in Asia, or Singapore, because Singapore during 40 years ago still a third world countries. So we try our best to start some journal and some book series in basic research in physics and mathematics. So this is how Journal A and Letter A started in 40 years ago. Thank you.
That I think it also not just Salam who convinced you, it is C.N. Yang who also supported you.
Yes.
Because, you need
Absolutely.
Yeah.
Absolutely true. So we also have the support from Professor C.N. Yang. Yeah.
Right.
And also S.S. Chung in mathematics.
Right. Yeah. Right. Okay. So to start with today's webinar, after having Professor KK Phua, we now will call on a good friend from National University of Singapore, NUS, with what is Professor O, True Hiap O, but in Singapore we just call him CHO. My friend CH, who I really know for many, many years as a high energy particle theorist. CH, now you have the floor to share on what World Scientific impacted on you and how you have contributed to spreading the horizon of physics. CH?
Let me extend my thanks to KK or Koku, okay, and also the World Scientific Publishing Company for having me at this remarkable occasion. We gather here today to celebrate not just the milestones, but legacy, the 40 years of the International Journal of Modern Physics A, or so-called IJMPA, and Modern Physics Letters A, MPLA. So it is both an honor and a privilege to share a few thoughts on these significant events. So when KK and me knew each other since 1978, okay, it was a long time ago, and then he helps me a lot. So I know him very closely. So now I just say a few words about the beginning of this journal and so on. So as KK said, okay, the World Scientific, the WSPC, the inception is about 1980, okay. So in 1980, the World Scientific have carved out a unique niche in the world of scientific publishing company. And then initially, the company focused on publishing monographs, as well as proceeding from conference and workshops. But KK is very good. So I think after a few years, if I remember not wrong, it's 1984. He started to talk to a few colleagues in NUS and other people and so on. Okay, so about in 1984, KK sensed, okay, and recognized that there's a need, okay, or necessity for a international journal that could serve researchers across the globe, in particular, including those from developing countries, especially in the Asia Pacific region. So this is a vision, a very ambitious vision at that time, okay? And in fact, I would say it's audacious, because at that time, the competitive landscape of astrophysics journal, renowned publications such as Nuclear Physics, Physics Report, Physics Letter, okay, Zycic Physics, Nuevo and so on, okay, were very well established and entrenched in Europe. And in the United States, the illustrious Physical Review series and also Journal of Mathematical Physics already set up the standard for scientific rigor and prestige. So each of these journals, if you notice, okay, is mostly supported by powerful physics societies and also the established publishing houses, and making their influence and reach formidable. So that was in 1980 situation. So venturing into this very competitive arena was not a small feat for a new publishing company like World Scientific Publishing Companies. So there are many challenges. So the challenge are many. So when KK conceived of this start new journal, I think we can imagine at the time, there are many things he had to overcome, okay? And I just list a few, okay? Like defining the journal aims and the scopes. And then important, he has to assemble a distinguished editorial board. This, everybody knows is important, the editorial board. And also establish a procedure, a robust and transparent peer review process. Furthermore, okay, he had to attract high quality research manuscripts. And furthermore, okay, the task of enlisting a reliable pool of referees was critical to maintaining the integrity and quality of the publications. So despite these daunting challenges, KK, okay, unwavering determination, exceptional vision, and remarkable fortitude led to the successful launch of IJMPA and MPA and MPLA in 1985. So within 1 or 2 years, he could manage to do this. That is a Herculean task. And this journal is not the same, okay? There's something, okay? And then this thing I would like to highlight. So this journal distinguished themselves from their contemporaries by not only publishing original research paper of high caliber, but also in every issue, including mini review articles. This special feature, okay, including this mini review article, in fact, proved to be invaluable, especially in an era when new subfields of physics were emerging, okay, at an unprecedented pace. The inclusion of these accessible reviews allow researchers to stay informed about the latest development and advancement, bridging the knowledge gap that often exists in rapidly evolving scientific disciplines. So this particular feature, you don't see it at that time anyway, for like physical review or nuclear physics. So this mini review, in my opinion, are invaluable, very helpful for researcher and even the expert, okay, because there are many fields emerging at that time, okay. So I would say, okay, the IJMPA and MPLA also hold the distinction of being the first major physics journals published in Asia, the first major physics journal published in Asia. There are some, okay, but I think I would say this is the major. And the significance and impact extend far beyond mere publication. They have provided a platform for physicists in Asia and the developing world, fostering collaboration, sharing knowledge, and promoting innovation. The contribution of these journals cannot be overstated. They have empowered countless researchers and have played a crucial role in advancing the global scientific community. In conclusion, as we celebrate this remarkable 40 years journey of IJMPA and MPLA, let us acknowledge the vision, hard work, and resilience that have brought this journal to life. They stand as a testament to what can be achieved and what we dare to dream big and remain committed to fostering scientific inquiry and collaboration across borders. So thanks again, KK, Koku, and the World Scientific Publishing Company for this incredible milestone, and here's to be continued success and influence of IJMPA and MPLA in the years to come. Thank you.
Yeah.
Thank you, CH, for such a very strong endorsement of what Koku has been able to do with World Scientific. And actually, CHO Choo Hiap mentioned about this Novocimento. And I want to remind people, because C.N. Yang, in one of his articles, did point this out. You remember four fermion theory? When Fermi first proposed this four fermion theory, he submitted it to Nature in 1933. You know, Nature is like what? Physical Review, or more than Physical Review of today, right? Yeah. It is the most impressive, impactful journal. Submitted to Nature, and Nature says, no, it is too, it's non-proven. It is something, they said something, I forgot the exact words. So what Fermi then did is to submit it to Novocimento, which is at that time a small, local journal. And what Fermi afterwards would always advise all of his postdocs and all of his young physicists around to say, do not be dejected because you were rejected. Because if you're a young researcher and you did not get yours published someplace, you become dejected, right? He says, do not. You now submit it to someplace else. And if it is indeed something very catching, Pauli read that article, and then Pauli now says, oh, that is the correct way, the four fermion theory. So this is something to remind and to advise everyone that indeed do not be rejected by the big guys. Go with the other small guys who are willing to help you and to broaden the horizon of physics. All right. And then just to conclude, I would just want to remind everybody to give some credit to CH himself, that he was chairman of the physics department from, 2000 to 2008. And during that time, he was the founding director of CQT, which is the Center for Quantum Technology, which now is a very big, center all around the world, because quantum technology is now taking over all of the new world of science. So it is just a good credit to my friend, colleague, CH. So now, without further ado, let me now just quickly introduce my friend, Kazuo Fujikawa.
Yeah.
Yes, he is a PhD from Princeton under Sam Treman. And we all know who is Sam Treman.
Yeah.
In 1970, and he became professor of Hiroshima University, Yokohama Institute, University of Tokyo, Nihon University, RIKEN. I mean, there are all these, right? But what is also very interesting is that he is 1986 winner of Nishina Prize. And we all know who is Nishina. So now, without further ado, let me now give the floor to my good friend and colleague, Kazuo Fujikawa-san.
Yeah. Thank you very much for the kind introduction. And I'd like to use the transparency. Okay.
Yes.
And CHO introduced you the International Journal of Modern Physics A and Modern Physics Letters A, and this is a 40th anniversary this year. So I should first say congratulations on the 40th anniversary of International Journal of Modern Physics A and Modern Physics Letters A, published by World Scientific. And these two journals accepted even those papers which may sometimes look too provocative or drastic in their assertions. So it is very important to have journals where you can express your own opinions freely. And this aspect is very important from the Japanese point of view, because I found many Japanese people published very interesting new ideas in those journals. And I myself also published many papers in these journals. And today, I'd like to mention one of the papers, that topological properties of various phase. This is my first paper on this subject, written about 20 years ago. And so, because CHO explained some history of the journal, I'd like to talk on some physics aspect, okay? And the level crossing problem is described by the Hamiltonian with a slowly varying variables and single particle theory. And in the second quantized notation, this problem is derived this way, namely the instantaneous energy eigenvalue, and then some factor between in terms of the instantaneous wave functions. This is often called the geometric parts. But in the second quantized formulation, this appears as a part of Hamiltonian. Therefore, you can just diagonalize the Hamiltonian, then you can learn everything, okay? So instead of separating kinematic part and the phase, but everything is part of the Hamiltonian. So this is the advantage of second part quantization scheme. And then one can first consider the adiabatic approximation. This is a diagonal dominance, and well-known works are Longet-Higgins and Berry. Okay. So you can just take the diagonal part of this part, so energy part. Okay. And then it is well known that this part gives a monopole-like singularity, namely two level crossing point. And if you consider level 1 and level 2, then this phase or this kinematical phase part becomes just these two parts. So 1 plus cosine theta divided by 2 and phi dot, and this minus 1. Therefore, this one, if the Hamiltonian has this part, then you can find the phase factor if we integrate over time. And then I pi times 1 plus minus cosine theta, these two gives. So this gives a monopole type singularity. And cosine theta 0 corresponds to the so-called Longet-Higgins phase change rule, because I pi means just plus minus 1. So this is 1, okay? So this is a well-known works and well-known part. And my contribution in this paper is that diagonalize the phase terms in the level crossing problem. So this is a non-adiabatic approach. Therefore, if you look at only two levels which are crossing, then these two are the main energy parts, and these two are the geometric phase part. And then important point is that in the adiabatic approximation, you have these two terms. But eigenvalue means some of them are eigenvalue. And one of them becomes just phi dot. Therefore, one of them 1 and the other is 0 eigenvalue. Therefore, from the point of view of the non-adiabatic approach, just diagonalize the phase terms. Then these two are the so-called geometric terms. And these two are the energy terms. And because we are operating in the finite time interval, because of uncertainty relation means there's some energy split into these terms, and then two phase terms. And this uncertainty relation based on this one gives 1/2 h bar. This kinematic term becomes the integration over 0 to pi corresponds to 2 pi h bar, therefore about 10 times bigger. But anyway, geometric phase term becomes just this becomes 2 pi I or 0. Therefore, all is unity. So this means no monopole terms in the level crossing point, and no Longet-Higgins phase change rule in this formulation. And this is very natural, I think, because we are working on the regular Hamiltonian. Therefore, no place to have the singularity. Okay? Therefore, naturally, no monopoles and no phase change rule. Therefore, in a sense, these two notions are artifacts of the adiabatic approximation, you may say, okay? But at the true a level crossing point. If like at the very closest, no monopole, no phase change rule. And later, I wrote many papers on this related subject. And the most recent paper is this Japanese journal, and 223, that the Berry's phase and the quantum mechanical formulation of anomalous Hall effect. And these are the brief summary of the paper I published in Modern Physics Letters A 20 years ago. And this is the first paper on Berry's phase I wrote. But since then, I wrote many, many papers on this subject. And most recent one is this one. And so finally, I would like to say that the International Modern Physics A and Modern Physics Letters A, many happy returns of the day. So to prosper furthermore years. Thank you. That's
Thank
my
you.
all. Yeah.
Thank you, Kazuo. It's a very technical paper, and anybody who really wants to read more into it should go into the journal, Modern Physics Letters Journal A.
Yeah.
19, published in 2005.
Yeah.
And there are others also. So it is good for all of anyone on the audience who is interested to actually dig into it, because when someone presents it within 10 minutes, it's a little too much for anybody to really fully grasp. So it is important that there is a journal where you have ability to dig into it. All right. So now we will go to our friend in Rutherford Appleton Laboratory in UK, Hong-Mo Chan, a good, famous theoretical physicist who has this very important concept called framed standard model. And maybe it would be good to have Professor Hong-Mo give a review or introduction to what is behind this very important concept, which in fact has come over into gauge theory with Yang-Mills theory. So, Hong-Mo?
Thank you for introducing me, which I don't deserve, but I'm also very bad in IT connection, so I may have difficulty joining you, but I shall try. Okay. The title of my talk today is a frame standard model whereby 3 old problems of the standard model and 1 beyond appear solvable or resolved. And it's a joint work by Jose Bordes, Florence Choo, and myself. As we know, the standard model, in spite of all its successes, has 3 problems, or more than 3 problems, in fact. The 3 outstanding problems are the generation problem, why there should exist 3 generations, only 3 generations, quarks and leptons, and secondly, why hierarchical masses and mixing pattern. The second problem is a strong CP problem. Color gauge invariants allow theta angle term, the quantity of the following form: C prevailing term of topological origin. And if you take theta equal to 1 between 0 and 2 pi, implies an electric dipole moment for neutrons 10 to the 9th, a billion times larger than experiment. So definitely wrong. In the standard model, theta I is just put arbitrarily to 0. The third problem we only discussed is the dark matter problem. Experiment says about 78% of the universe is dark, but the standard model accounts only for about 20% of the luminous matter. The so-called frame standard model that we worked on is constructed initially to address the problem A, that is the generation problem, but it turns out it offers also byproduct solutions to B and C, that is the dark matter and the strong matter problem. The frame standard model is obtained by framing the standard model, similar in spirit to Vierbeins in gravity. just by promoting frame vectors in internal symmetry space, this internal symmetry, to dynamical field variables, which grow Fremons. Also similar to Vierbeins, Fremons carry an index for local frame as well as an index for a global reference frame. In other words, Fremons form double representation of the local symmetry G and its global dual tilde, like that. Explicitly, the frame standard model adds the usual gauge and matter fields of Smith's dynamical variable that follow scalar Lorentz scalar Fremon fields. First, a flavor Fremon, which basically just a dual color triplet times the standard Higgs field, and the color Fremon, which is a dual flavor doublet times a matrix, 3x3 matrix. In all applications so far, the triplet alpha can be taken as real, that is, a unit vector, 3 vector, a beta can be ignored. It seems to be the only representation of G cross G tilde that works. It happens also to require the smallest number of scalar fields added to the standard model. The FSM may thus be regarded as a minimally framed version of the standard model. And the FSM action is supposed to be invariant under G cross G tilde, doubly symmetric. Okay, we turn next to the generation problem A. You notice the flavor Fremon is just a usual Higgs field multiplied by alpha and gives the fermion mass matrix at the tree level as m times alpha dagger, where alpha from Fremon is common to all quarks and leptons, and only ms depends on the species. Now M is a 3x3 matrix, hence immediately you have 3 and only 3 generations of quarks and leptons. Solve one thing in the generation problem. Secondly, M is factorizable into 2 vectors. It's a rank 1, hence there's only one massive state and no mixing, which is not a bad approximation actually for quarks. But since the FSM action is explicit, you can calculate loops. And color Fremons, this 3x3 matrix, carry both the local and global indices. Hence, phi loops can change relative orientation of local to global frames, and causing alpha in the mass matrix M to rotate with changing scale. Hence, will affect the masses and state vectors of quarks and leptons, which each to be determined as their own mass scale. Hence, it follows the non-zero mixing and non-trivial CKM and PAMN matrices. And secondly, non-zero masses for lower generation by leakage from the heaviest, giving hierarchical mass patterns. For example, MT much greater than MC greater than MU. The renormalization group equation to one level gives a trajectory of alpha depending on 7 parameters, which when you use to fit the mass and mixing data gives the following result. I'm sure you have no time to look through the details of this, but you see that many of these things are fitted to within 1 sigma of the data, and the others are not too bad. All mass and mixing parameters were fitted with these 7 parameters, which replaces 17 in the standard model, and the fit is about as good as any we have seen. There are 2 special points to note. First, you notice the Yaoskov invariant, J, is order 10 to the minus 5. It's about the same experiment for input value of theta I close to pi. And second point is probably even more interesting. The trajectory has a vacuum transition, which we call VTR1, at around mu is equal to 17 MeV, which gives a point of inflection to the trajectory and leads to the result that Mu is greater than Md, a rather crucial result. Our own existence depends on this, despite the fact that MT is very much bigger than MB and MC is very much bigger than MS. And this VTR1 will figure later on also in the problem C and D below. Oh, by the way, the trajectory looks like this. It goes around and goes back, but I'm sure it's too unclear for you to see. Next, we turn to strong CP problem. I remind you the theta angle term is to CP violation much bigger than experiment. But in the FSM, M is equal to this factorizable has 0 modes perpendicular direction alpha. For 0 modes, relativities of the left-handed and right-handed side are defined, hence the action is invariant under a chiral transformation of these 0 mass fields. And chiral transformation gives infinite path into a factor of the same form as the theta angle term, thanks to Professor Fujikawa. We are therefore free to choose theta, this angle of chiral transformation, equal to minus theta I, and cancel, in fact, the theta angle term altogether. Hence, there's no CP problem solved, or in fact, no CP problem at all. The above can be done at every mu, every scale, in either direction perpendicular to alpha, and when alpha rotates, then only the new direction, the binomial trajectory, is allowed. When alpha rotates, however, nu rotates also, and hence, a surprise prediction of the FSM, the definition of CP depends on scale. And this has two important corollaries. The first one, that up and down quarks, or leptons, have different masses and different scales. Hence, the definition of CP differs for the up and down. And this leads to the Km phase in the CK matrix, which is tested in the above fit, and also leads to a prediction of delta CP for leptons in the PEM matrix. And this is tested in reference 203. The second corollary, which is quite important also, is that baryogenesis needs CP violation, but a standard model with CP violation only in the Km phase in the CK matrix is generally believed not to be enough to give the observed eta, the ratio of baryons to photons. The FSF, on the other hand, has a scale-dependent CP violation in that prediction above. It is found to be sufficient, we think, for inducing the observed value for eta. It's a paper with reference 4, which is in preparation. Okay, next we turn to the dark matter problem. The flavor Fremont is a usual Higgs field, but the color Fremont phi is new, no analog in SM. Color is confined, which means phi cannot exist as free particles and has to form color neutral bound states via color confinement with phi dagger, for example, to give scalars and also vectors called X and G. It can also combine with color fermions to form co-quarks called Q and co-lepton L. And recall to Hopf's confinement picture of electroweak theory, you find that the H's analogs of the usual Higgs boson and the G's analogs of the vector bosons are Q, capital Q, are analogs of Q's, the quarks, and leptons are analogs of the leptons. A study was made on the mass spectra and couplings of these particles and found no direct link between hidden sector of H, G, Q, and L and the standard sector of the usual particles we know, except via the photon gamma, which is common to both sectors, and via the mixing between H plus, some member of the H, with a usual weak vector boson, and G8 with the usual vector bosons. And the two sectors, hidden and sector, are mirrors of each other under interchange of roles between color and flavor. The hidden sector is more populated than standard sector. The Fremont degree of freedom is in ratio 9 to 2. That is about 78% to 22%. And this is nearly identical to the ratio of dark to ordinary matter in the PDG. Quite interesting point to note. So one is tempted then to identify the dark matter on to the neutral remnant of the hidden sector. We have found no means yet to study directly the hidden sector. It will take time, I think, because we know so little about the hidden sector. But we have explored at the interface. There's a mixing of the G8 with this, and also the mixing of X mentioned above. The mixing of G8 with vectors give a prediction that MW should be bigger than what is predicted by the standard model. This is explored in reference 6. And the mixing between this gives rise to anomalies around the 17 MeV, a vacuum transition point. And this can occur then in the G-2 anomaly, in the so-called lamp shift anomaly, in the atom key anomaly, which is G peak 17 MeV, and also a B decay anomaly, or absence thereof. And these are investigated in reference 7 and 8. Consistent with experiments found so far, but it should be warned that data is still very fluid in this thing. So, okay, FSM has something to say about all the 3 problems you mentioned in the standard model. We happen also to have something to say also about the horizon problem in cosmology. The problem, stated briefly, cosmological microwave background is known to be isotropic uniform to an accuracy of 10 to the -5. But when created, when its age was about 500,000 years old, the universe was divided in many causally disconnected parts. Hence, the whole universe must have been in causal contact within a single horizon at some time in the distant past. The question is when and how? Now, there's at first sight apparent unconnected tract in the FSM. The vacuum transition was mentioned several times already. At 17 MeV, a 2-dimensional dual color space collapsed to 0. This comes about as follows. The vacuum expectation of phi, or in other words, the color frame vectors, are of this form, where R is a ratio between 2 couplings, which approaches 1 at the transition point VTR1. Hence, the metric, which is phi delta phi in dual color space, has 2 diagonal entries which goes to 0 at the. Now, if you imagine the internal symmetry space in FSM is embedded in space-time in Kaluza-Klein fraction, then when you compress in one direction, the universe would expand in another to compensate, like an air balloon with air replaced by background radiation. Thus, you have a ratio, a relation like that. Then if we put from early estimate that the size of the dual color space is around 2 TeV, and you place 0 to place the Planck length, the universe will expand in space direction by a factor, I think, if I remember correctly, 10 to 11. And this is enough when extrapolated backwards to bring the universe back into a single horizon. That's all parts into causal contact and overcome the main obstruction in the horizon problem. Okay. To conclude, or rather just some remarks, it seems the FSM may offer, and may have offered already, solutions to A, B, and C, and D. Those solutions to C and D are only tentative, only indicative, but those indications in the A and B generation and the strong CP problem, indications are getting quite strong that maybe solution it may be at hand. In addition to solving this problem, or helping to solve this problem, the FSM has predicted, given 2 very surprising predictions, which is likely to be far-reaching consequences. First is that definition of CP depends on scale. And secondly, there may be a vacuum transition at 17 MeV, setting a new physical scale of energy and of length. I think I've overrun my time by a few minutes. But here's a reference for those of you who might be interested. Thank you.
Now, in listening to all of that, when you hear about all of the potential things that FSM can solve, it actually comforts you to think, to remember when the first Higgs proposal, right, was submitted by Englert and Higgins. It took a long time for the world to really fully understand the potential impact. FSM is such an important concept, but it takes time for the experiments, for the world to fully establish what FSM can mean. And it is good that we have had this opportunity to see and learn about the potentialities of FSM. And maybe one day the world can fully understand this cosmological expansion. Oh, how did it begin? And when did it begin? All these are interesting questions that we as scientists have to answer. But until you have a full understanding in the theoretical framework, you cannot really understand it. But the fact that we have this HONMO's, FSM model, which was proposed in, 2012, that indeed there will be one day the world can fully appreciate and want to give praise and thanks to HONMO for his, beyond the horizon idea. Okay? Yeah. Now, the next speaker was scheduled to be Goran Sanjanovic. And I wanted to sort of mention what his impact is, even though he sent us an email just within 30 minutes ago that he cannot because he's sick. He is absolutely, not possible. But it does not mean that we should glide over it. You know why? Because Goran Sanjanovic got his PhD at CCNY. And he got it under R.N. Mohapatra. You know who is Mohapatra? He was a professor at the City College from 1974 to 1976. But Sanjanovic was the first PhD student under Mohapatra. And the work that Sanjanovic did has to do with something known as seesaw mechanism, which he proposed with Mohapatra in 1979, independent of Peter Minkowski, Sheldon Glashow, Murray Gell-Mann, Pierre Ramon, Richard Stansky, and Yanagida. In other words, Sanjanovic was working with Pati, Yogesh Pati, and Abdul Salam with Pati at the University of Maryland. And it is truly a very important concept of left-right symmetric theory of electroweak introduction. The fact that he was not able to come, I really would have liked so much for him to say something, especially since when I knew him, he was a young little man, but now he is, maybe not as old as I, but, but it's good to mention what Sanjanovic is, because the next speaker is also a CCNY graduate, and he was a graduate in 1979 under distinguished Professor Bunji Sakita at CCNY. Well, after graduating, he was a postdoc at Chicago under Nambu. We all know who is Nambu, right? And then he joined Tata Institute in India. And he was the chair of the theoretical physics department from 2007 to 2009, became the distinguished professor 2008 to 2015. And presently, he is the Infosys Homi Bhabra Chair Professor of this Tata Institute, founding director of International Center of Theoretical Science at Tata Institute. And he is the recipient of 2004 TWAS Prize in Physics, the 1995 Physics Prize of the International Center for Theoretical Physics, and the J.C. Bose Fellowship of the Government of India. It is my pleasure to introduce a former graduate student of CCNY who will now share on what the impact of World Scientific has been in his life. Spenta?
I Hello, everybody. Thank you, Ngee-Pong, for these very kind words. I'm very honored and very touched to be invited to be part of this meeting celebrating 40 years of World Scientific Journals. So I've had a long and productive association with World Scientific, almost since its inception in 1985 by Professor K.K. Phua, affectionately known to all of us as KK, and his wife, Miss Doreen Liu. The journals, International Journal of Modern Physics and Modern Physics Letters A, were launched in 1986, followed, of course, by many others in the subsequent years. Having returned to India in 1982 from the University of Chicago, I was very pleased to witness the emergence of an Asian-based international publishing house. The word international is very important, actually, because there have been a lot of publishing houses in Asia, and society, journals, etc. But I think this was the first major international publishing house which was envisioned by KK and Doreen. In my view, this development offered a much needed counterbalance to the long-standing dominance of scientific publishing by Western companies and societies. I have always been very acutely aware of the historical role that scientific journals have played in the advancement of modern science over the past 400 plus years. For example, starting from the philosophical transactions of the Royal Society of London to journals like the Physical Review of the American Physical Society. I think these societies and these journals have played a very important role in what I would say has been a dominance of Western science and over the other societies actually who in the past have had great flourishing cultures like India, China, Middle East, etc. So it was therefore both an honor and a privilege for me to be associated with this pioneering enterprise. I served on the editorial boards of both these journals almost from their inception. And in the early years, I made many memorable visits to Singapore to meet with KK and his team. And I'm very gratified that they valued my thoughts and suggestions. So, I strongly believe that, verbal support has to be sort of, matched by action. So I began myself publishing in World Scientific Journals and encouraged, especially when I was at the Institute for Advanced Studies in Princeton for a couple of years, to publish in the same Asian journals. And to date, I have myself published 22 research papers in IJMPA and MPLA. And among these is my most cited paper written at the Institute for Advanced Studies in Princeton in 1991 on the discovery of the black hole in two-dimensional string theory, which was published in MPLA. Beyond journal articles, I have also served as an editor of 6 books published by World Scientific. None of this would have been possible without KK's support and confidence in me, and for that I am deeply grateful. It has been a long and fruitful relationship, and one that has encouraged and supported us, especially in India, in many ways. As I close, I would like to wish World Scientific and its journals continued success in the years ahead. But I would also like to make a final plea. Please consider making MPLA and IJMPA open access journals. A great first step would be to make the first 25 years of content freely available. This would be a meaningful service to the scientific community, particularly across Asia,
and would further enhance the reach and legacy of World Scientific. Thank you very much once again for inviting me, and all the very best. Thanks.
Thank you, Spenta, for encouraging all the young scientists in Asia to indeed rely on World Scientific to broadcast all of their new research ideas, whether they are drastic, whether they are beyond the horizon, anything that is something that is new, it would somewhere be read by other people, not just in America, in Europe, but also in Asia. And I'm very pleased and glad that World Scientific has not kept to just simply prints of printed journals, but also have e-journals access, because it's important. If you are from somewhere in Thailand or, Myanmar, and you still have an interest in physics, you cannot access to buy the book or the journal, but that you can then access e-journal. So World Scientific is also evolving with the whole world of publication to not just have solid journals and books, but also to have e-journals and e-books. So thank you, Spenta, for emphasizing this and encouraging more of the people listening or watching. So next, we have the pleasure of inviting the next speaker, who is also from India, is Manmohan Gupta, Professor of Physics at Panjab University, Chandigarh, India. He is a member of the Physical Sciences Research Committee of CSIR, the government of India, since March 2008 to now. And he has been also a member of the editorial board of World Scientific. And it would be good to now hear from Manmohan what is the impact of World Scientific, the International Journal of Modern Physics A and the Modern Physics Letters A. Manmohan?
Let me first thank Professor Phua and Professor Chang for giving me this opportunity to be part of this distinguished panel for celebrating 40 very successful years of International Journal of Modern Physics A and Modern Physics Letter A. No, I would first discuss, I have had a very long association, almost of 30 years, but there are some very interesting things which I would think would motivate the younger audience, how I got into this IJMPA. That is what I would like to emphasize. See, I would start, I had some bizarre experience with physical review letters, physical review D, and physics letters. And those bizarre experiences would give me opportunity how I discovered International Journal of Modern Physics. See, first let me start with the physical review letter. See, in the 80s, late 80s, it was decided, it was almost, most of the theoreticians were speculating that the T quark mass is around 60 GeV, 60 to 70 GeV, or 50 plus, something of that sort. So I had started working on this CKM phenomenology at that time, and I had seen the calculations, this lattice gauge calculations, and then some new data emerging from B decays. Now, using some simple phenomenology, I was able to deduce that the T quark mass has to be more than 120 GeV, and it could go up to 160 GeV. Now, that was very startling. So initially, I was very hesitant to submit. Ultimately, I thought I must submit to physical review letter, because this is the problem which everyone is talking about. I submitted the paper to physical review letter. Now, for 4 to 6 months, I didn't get any reply. After 6 months, the response comes that there is nothing wrong with the paper, but the data has changed, and we can't publish in physical review letters. However, we can publish in physical review D. I was a very young person at that time, thought that, okay, so let physical review D may also be good. And from publishing from India is not that easy. I requested, okay, publish in physical review D. But again, after some time, I got the response that there are several issues with the paper, so it cannot be published. I withdrew the paper and published in some Indian journal, Pramana, which is a very good journal. However, it lacks the reach and the visibility in the international domain. Then I had experience with physics letters B. I submitted a paper which was based on a paper published in physics letters B. After 2 months, I got the response that there is nothing wrong with the paper. However, the paper on which it is based should not have been published. Now, if you apply this kind of subjective criteria, I do not know how many papers would have been rejected out of hand. So it was a big frustration. And then again, I tried my luck with physical review about something which was new. So Harold Fritsch had proposed a model about reproducing the CKM parameter, particularly the Cabibbo angle. So we found that the latest data was not fitting the Harold Fritsch model. So therefore, we decided to extend the model. And I did a lot of calculations, submitted the paper to physical review. So after 3 to 4 months, paper was rejected and sent back to me. But after a couple of weeks, I found that a similar paper is published in Physical Review D. So I wrote back, I say, well, my paper was received earlier than the paper which is already published in Physical Review D. So therefore, my paper should also be published. There was a lot of communication back and forth. So it went on and on. Ultimately, the whole discussion went up to the level of the Vice President of the American Physical Society. And he just wrote one line that the paper lacks sufficient originality. Now, this was also very disheartening. Now, if you apply this criteria, subjective criteria, I think 95% of the papers would all be thrown out of the journals. So this frustrated me completely. Then somebody suggested that if you have some idea, interesting idea, you better publish in International Journal of Modern Physics. So I tried my luck there and it was successful. And after that, I started publishing, of course, in all journals, including International Journal of Modern Physics, MPLA also. And then, of course, as I was publishing there, so I became referee also of those journals. For almost 20 years, I have been refereeing physics literature. No, of course, again, I'm thankful to Professor Phua and Chang for making me member of the editorial board. So this is my journey with the International Journal of Modern Physics. And I would suggest the younger audience that if you have something which is out of box, which is different, then publish it in International Journal of Modern Physics. I find the refereeing very constructive. The referees, whosoever is there, they are very positive in their response. And then it gives us opportunity from the Asia Pacific region also. So that also. In fact, I had another bizarre experience with the European journal. I had submitted the paper and the editor sends me back, see, you publish it elsewhere. So I was very disheartening that how can they take such a subjective decision? Not that they would take some objective decision also, but this was something I never thought, that the editor would just say that I should publish it somewhere else. This was something not acceptable. So my journey, I would say that whatever experience I have with the International Journal of Modern Physics and MPLA, they have been very constructive, very positive, and I'm very happy to be associated with that. In fact, I would say that for the last 40 years, the journals have progressed. These two journals have progressed very well. In fact, I wouldn't like to name and go into the detail. Many journals have vanished or they have been merged into other journals, including very famous journal, this Progress of Theoretical Physics, started by Hideki Yukawa. A very prestigious journal. Now it is a part of another journal. But international journals, this IJMPA and MPLA, they stand on their own feet, and I think they are flourishing. As I had read whatever material was sent, I think they are done really well. And of course, the quality of papers which are being published, they are also really good, and they are going up. And I have no doubt that in coming years, these journals can really be competing with the best in the Europe, because they're very objective. That's probably more important. I have never seen any, see, I've given a couple of experience, this kind of, you can say, very subjective kind of interpretation or opinion about publication of papers. You can reject a paper based on solid logic, but to say that the paper lacks sufficient originality after 6 months or 8 months, this looks ridiculous. Anyway, I have some suggestions also, because I would say that I personally feel that the journal needs to really come to the knowledge of most of the people. See, the Singapore used to host conferences in particle physics and cosmology. They were a very good meeting point for scientists all over the world, particularly of the Asia Pacific region. So that was some kind of fostering, you can say, bond between several countries. So those, I think that conference circuit needs to be revived so that the journal also gets some kind of, you can say, visibility, as well as we interact with people from the lesser known countries. And that is where we can promote that this is how we should try to push the Asia Pacific this publication, Singapore publication. I would also suggest that the Singapore publication should be working on research metrics also. Because if you see the two well-known publishing houses, the Elsewhere and the World of Science, both have their own research metrics. And I have done some work. I had written an article on that. Based on that, I found that there is always some kind of bias. There is always some kind of emphasis. So the Singapore publication can also have a look at that. And I'm sure that they can also devise a more conducive, you can say, parameter which quantify the journals. So that is another thing which I would suggest is that, see, these days, if you look at the physics scenario, most of the space is occupied by the material science. At least in India, I find that almost 90% papers are being published from material science. And this is creating a lot of, you can say, imbalancing in the, you can say, in the physics domain. I think the journal can proactively participate in this, that material science is important, but other sciences like particle physics, cosmology, which have been very old, and they have made seminal contribution in the development of science, they should also be there much on the table. And particularly in some of the, again, the domain of this two journal is particle physics, cosmology, gravitation, etc. I think there are several countries in the Asia Pacific zone where these subjects do not get any prominence. So the Singapore publication, which has a very good reach, and they can think on this issue also, so that this region, which is very active, China, India, of course, are very active. And there, of course, I don't consider Japan and Australia, they are part of the developed world, but India and China have really come up, and I think in 10 years, they can really outshine all other countries. So therefore, if some efforts are made, I'm sure that these two journals can really be part of the topmost journal. So with these remarks, I would once again congratulate the organizers of this conference, as well as the two journals, for their very happy journey, for their very prosperous journey, for very, you can say, something which they have done, which was very difficult. And I must thank Professor Phua for being taking it at the almost at the top level. So thanks once again to both of you for giving me this opportunity to be part of this distinguished panel. Thank you very much.
Thank you, Manmohan. In fact, you made many suggestions, but it will have to be up to KK and the World Scientific Company to see how to implement, because the world has changed, and with all of this tariff, war, it really has upset everybody, right? So we'll have to see. But it was very good. You have made very good,
I can send the detailed views also on these, some of the suggestions, if they are needed.
Well, okay. All right. So now the next speaker is Shaolan Wu Shaolan, who is the Enrico Fermi Distinguished Professor of Physics at University of Wisconsin in Madison. And she made very important contributions towards gluon. There is Wu Shaolan. She cannot join us, but she has recorded something. But before we play the recording, I just want to sort of give some background to her, because there is something very special which I will come to. She is not just the Enrico Fermi Distinguished Professor, but she actually did the first work for the gluon, because she was part of this Petra accelerator at Daisy in Hamburg. And there they actually were able to see a sign of what is called the gluon. And she was a member of also the CERN Large Hadron Collider, LHC, ATLAS. She was the first US participant in this ATLAS collaboration, which is the discovery of the Higgs boson, which we all know really revolutionized the whole world, the understanding. And it's called the standard model now. and she was awarded the 1995 European Physical Society High Energy and Particle Physics Prize. But now here is something I discovered. She also has a planet named after her. You know, you think that, oh, you are so famous, you are a star of this world. There is a planet number 177770 Sao Lam Wu. It was discovered by the astronomers with the Mount Lemmon survey in 2005, and it was named in her honor. And so it is truly an honor to now introduce Professor Sao Lam Wu, and she could not be present on video, but she has recorded a recording. So can World Scientific now play the recording with her picture?
Hello, Professor K.K. Phua, friends and colleagues. It is a great honor for me to speak today on this special occasion, the 40th anniversary of International Journal of Modern Physics A and Modern Physics Letter A. These two journals have long served the global physics community with distinction, vision, and integrity. While we are gathering here to celebrate this important milestone, I want to extend my deepest gratitude, both personally and on behalf of my late husband, Professor Taichung Wu, for the extraordinary role that the World Scientific Publishing has played in advancing worldwide scientific communication. World Scientific has been more than a publisher for us. It has been a trusted partner in our research journey. Over the years, it has provided us with a platform to share our discoveries, ideas, and aspirations with the global scientific community. My husband and I have been privileged to publish many of our important work in IJMPA. Thanks to Professor Phua's unwavering support and leadership, IJMPA became a place where our ideas could take shape and reach a wide audience, whether theoretical explorations or experimental studies, and reflection on the key discoveries in particle physics. Let me begin with my late husband, Taichung Wu, who passed away last year on July 19, 2024. Until his very last days, he remained passionately engaged with physics, and World Scientific was there with him until the end. In November 2023, he published what would be his final research paper, Concept of the Basic Standard Model and a Relation between the three gauge coupling constants in IJMPA. In that work, he sought to reduce the parameters of the Standard Model and uncovered a remarkable relation among the three gauge coupling constants. It advances the elegance of our understanding of the fundamental forces. This work of his intellectual farewell was something he was truly proud of. Between its publication in November 2023 and the time shortly after his passing in July 2024, this paper was downloaded more than 12,900 times in less than a year. This is a testament to both the scientific value of his work and the reach of the journal he trusted. I am immensely grateful to Professor Phua and to World Scientific for the decision to publish in the coming months a memorial volume in honor of Taichung Wu. This memorial volume features analysis of his 400 publications. It reflects his childhood and formative years and the celebration of his scientific legacy. It also includes photos of his happy days with his family and collaborators. It includes a contribution of remembrances from his family, friends, and colleagues. This publication of Taichung Wu's memorial volume is a gesture that means more to me than I can express in words. I know that Taichung in heaven is deeply touched by this. I would also like to take a moment to reflect on my own research journey with World Scientific. In my career as an experimental particle physicist, I have focused on different discoveries. I have been fortunate to participate in the discovery of the gluon, which is the first Yang-Mills boson, and later the discovery of the Higgs boson. The discovery of the Higgs boson culminated decades of searching and the effort of thousands of scientists. Both of these breakthroughs hold a special place in my heart, and I published multiple articles on these discoveries in World Scientific's International Journal of Modern Physics A. My article, Discovery of the First Yang-Mills particle, the gluon, traces the early days of this work. It was a personal journey, but also a deeply collective one. I am glad that this story, published by World Scientific, as well as brief history for the search and discovery of the Higgs particle, could be shared with the community in such a thoughtful and accessible forum. For me, physics have always been a lifelong calling, and I have tried to reflect on that path by presenting it in my commencement address I gave at Vassar College in 2014. The title was From Vassar to the Discovery of the Higgs Particle. The publication of this speech found its home at World Scientific IJMPA. Professor Phua has never hesitated to honor just vigorous technical achievements but also the human story behind them. I want to say to Professor Phua and the other leadership of World Scientific Publishing, your legacy is profound. You have built bridges across generations, giving voice to both young and established scientists. You recognize that science needs more than just idea, but you also need platform. Through World Scientific, you have provided an outstanding platform. As we celebrate 40 years of IJMPA and MPLA, I thank Professor Phua deeply for the decades of tireless work you have poured into these journals. You have not only shaped the landscape of scientific publishing, you have played an outstanding role in advancing modern physics. For all this, we are sincerely grateful. Thank you.
The next speaker is Alexander Migdal, NYU and the Institute for Advanced Study. Alexander Migdal has a long collaboration with Alexander Polyakov for a long, long time. And in a 1983 paper he wrote with Polyakov, is sort of like a precursor, what is now known as the Higgs mechanism. And they submitted it to Journal of Physics in Russia, JETP, and it was rejected. Only after 3 years, it was accepted in 1966. And then between 67 to 73, he worked with Gribov and again later with Polyakov on conformal bootstrap, which was a precursor to the seminal work by Kenneth Wilson, for the Nobel laureate in 1982. So he is a true expert on turbulence, on renormalization group study for quark confinement.
Duality of decaying turbulence to a soluble string theory. The revolution began in International Journal of Modern Physics A, 1994. The theory of turbulence I will present today began with my 94 paper, Loop Equations and Area Law in Turbulence. It's no coincidence that this journal was the first to welcome such a radical idea. The editors of IJMPA have long fostered openness to bold, unconventional thinking while maintaining high standard for theoretical rigor. At the time, my colleagues largely overlooked the theory. It would take 3 decades before the first confirmation of predicted area law from direct simulations by Srinivasan. Then, in 2023, the exact solution of the loop equations for decaying turbulence finally crystallized in my mind. I have since submitted a comprehensive review and new development of this theory to IJMPA to appear online later this month. The Hamiltonian systems satisfy the Liouville equation for the probability density in phase space. And based on this equation, theoretical physics conjecture the Gibbs distribution as the only conserved multiplicative measure. In dissipative systems, such as Navier-Stokes, the probability measure is not conserved but decays into a standstill with zero velocity. So the turbulence problem is to find decaying solution for the probability evolution to replace the Gibbs distribution, fundamental problem which exists for 200 years, but only now it has been solved. The loop average is defined as a characteristic function for the distribution of velocity circulation. Gamma is velocity circulation, integral of velocity around the loop, and psi, the loop functional, or loop average, is average exponential of imaginary factor times circulation. And average goes over all trajectories starting from initial one and maybe multiplicating, because we know such phenomena happens, that trajectories could bifurcate, or maybe there is a small noise which could be enhanced, and instead of one trajectory, we get the whole family, which ends up in statistical distribution. So that's the issue here, to find that distribution. So evolution equation for the loop average replaces the Liouville equation for dissipative system. The velocity dynamics is governed by incompressible Navier-Stokes equation, with vorticity being curl of velocity, and time derivative of velocity equals three terms. It's advection term, v cross omega, then diffusion term, which is viscosity times curl of omega, and then there is a forces from pressure. Actually, there is enthalpy, P plus V squared over 2. And then there is, of course, incompressibility equation, divergence of V equals 0. So the loop function satisfies key relation derived from this equation, with gradient terms integrating to 0. So time derivative of psi equals this line contour integral of two terms. The third one dropped. And the problem, of course, is translate that into some operator acting on the psi, so it will, the right side will become the right side of the Schrödinger equation. So indeed, that was done in my old work, and the loop equation, closed functional equation for loop average, has a form of Schrödinger equation with Hamiltonian, which is equal to line integral over the loop of some operator L, which is some algebraic function of operators of functional derivative with respect to C prime. So it is not a simple expression in terms of C, but a simple expression in terms of functional derivatives, which from the Hamiltonian dynamics means this Hamiltonian effectively depends only on conjugate on the canonical momentum, but not on canonical coordinate. That's a solvable class of Hamiltonians. And the plane wave is a solution. So it's superposition of exponentials of some unknown function P of t and theta integrated over the loop. And this P of theta must satisfy what I call momentum loop equation for that psi to satisfy Navier-Stokes. So Navier-Stokes translates into one-dimensional, singular, but one-dimensional theory of variable P, which time derivative is expressed in terms of its boundary values on the neighboring value -0 and +0. That's non-trivial, but solvable problem, as we shall see. So this function L appears to be third-degree rational function of values of momentum P at two neighboring points, and therefore time dependence can be exactly found. It's just 1 over square root of time. And the remaining non-trivial function f is determined by certain nonlinear boundary problem, which I learned how to solve. And here is the solution. We build a fractal curve, which consists of polygon mapped from the circle into physical space. F becomes a polygon with vertices given by this formula, rotation matrix omega times essentially the circle in xy plane. And these angles on the circle are beta, which is rational fraction of 2 pi, times sum of Ising-like variables plus minus 1. So it was proven that in the limit of large number of points, that solves that equation. And it geometrically means random walk on regular star polygons. These polygons with rational angle in terms of 2 pi are called regular star polygons, discovered in Middle Ages, but never really studied seriously. I mean, random walk was only now found. So it was validated using Mathematica, rigorously tested in collaboration with the mathematicians, and it is very significant because it establishes totally unexpected relation between classical turbulence and number theory through novel mechanism of spontaneous quantization. Why quantization? Because this randomness which we have here is not a continuous randomness, which was expected from the point of view of spontaneous stochastization. Stochastization would be enhancement of the initial, say thermal noise to some smooth noise which will affect the distribution, but this one is not a smooth noise. It's discrete randomness. And discrete randomness is something which cannot be expected from the smooth nonlinear equation like Navier-Stokes. That's totally new phenomenon. I call it spontaneous quantization. And here's verification of that by experiments. And what we found is that experiments depicted here by, that's recent experiments in 25 on a large lattice, 4,000 steps in each of the three directions. So the red dots with error bars, vertical error bars, are shown here on that plot, and the green curve is my theory prediction. So that perfectly fits all the data. And the most non-trivial part is that it also fits the time decay. This energy decays at some power of time, and it here is compared with power of length, and length is square root of time. Now, here we have effective index of the second moment of velocity field, very well-known quantity. Kolmogorov says this index is exactly 2/3 and doesn't depend on scale, but we'll see that it does depend on scale in a nonlinear fashion. This green curve is my theoretical universal curve, which is number theory curve, no free parameters to fit. And the red dots, red data are simulations, and they perfectly fit my theory. My theory goes through all the data. So we conclude that there is basically no contradiction between my theory. It's totally confirmed by numerical experiments. And Kolmogorov theory is totally refuted. Forget Kolmogorov theory. It doesn't apply to decaying turbulence. Now, another thing are physical experiments, which measured in the 60s of last century, that energy decays as time to the minus 1.25, and I exactly predict that. My prediction is 5/4. So there is total agreement, and that basically leads to equivalence between decaying turbulence and soluble string theory, offers new perspective on geometric flow, provides tools for analyzing various new kind of problems, the magnetic hydrodynamics, turbulent mixing, etc., etc. And there are also Young-Mills gradient flows, which are very exciting new developments. So collaboration with the mathematicians, experimentalists, and DNS researchers now is welcome. I mean, it's very important to extend this theory. This is a breakthrough in mathematical physics. So it's a very exciting moment. It all started at IJMPA. Thank you.
Thank you to Alexander Mikdal. It's 4 a.m. there, or 5 a.m. there. But in any case, I think we've had a very interesting presentation by so many different people of what the impact is, world scientific, on each and every one of us, whether it is personal, whether it is simply recognizing how world scientific has broadened the horizon by encouraging all the young scientists and not so young scientists to publish their new ideas that will enable the world horizon of physics to actually grow, because we need to be beyond the box. When you're checking on something beyond the box, you better make sure that everything is correct inside the box so that you can then predict what is outside the box. And one last comment I will make is, when we get to know these famous stars like Xian Yang, like T.T. Wu, which we didn't really have a full time to discuss, when we learn about all of their ideas, it's good that we also be encouraged how to truly make sure that what we want to say is correct, but it is beyond the horizon. Let us look beyond the horizon and let us continue to learn what science can teach us about what is the future. So I know it's kind of getting late. Are there any particular comments, or we will just simply say good day, good evening, good night to everyone, and hopefully the recording of the whole webinar is put on World Scientific so that those who could not join us can nonetheless hear what has been discussed. Okay? Good day. and good night, good morning to everyone. Bye. See you sometime.